Have you ever found yourself, pulling up your phone to navigate the most efficient route? Or maybe managing resources for a big project?
Yeah, or even just wondering how something like the internet actually works, how it all connects so smoothly.
Exactly. It really makes you wonder, how does this sort of invisible hand of optimization guide so many parts of our modern world?
hmm
Well, today we're doing a deep dive into the fascinating field of network optimization.
And for this, we're looking at a really foundational text, Dmitri Bertsekas' Network Optimization. Continuous and Discrete Models. It came out back in 1998, but it's still incredibly relevant.
Right. And Bertsekas himself, I mean, his background is quite something. MIT PhD, started in engineering back in Greece.
Yeah, and his work in this specific area, it spans decades. What's really interesting about this book, I think, is that it's not just theory. It's deeply rooted in his own personal research.
So actual contributions and collaborations he was directly involved in.
Exactly. It makes the insights feel very earned. It's built from the ground up through his work.
Okay, so our mission today for you listening is basically to give you a shortcut. We want to unpack the core ideas, the maybe surprising connections, and the real-world implications of network optimization.
Right, without getting totally lost in the heavy mathematics.
Let's try it. Anyway, so where do we start?
Well, Bertsekas makes this really central point right away. He says network optimization sits uniquely in the middle of the Great Divide,
The divide between what exactly?
between continuous optimization problems and discrete ones.
Uh-huh.
It sort of bridges the gap between these two major types of problems.
Okay, and why is that bridge so strong? What makes network problems special in that way?
It's because of something called the extreme points. These are like the corner points, the potential solutions within the constraints of the network problem.
Uh-huh.
And the fascinating thing is, these points, these solutions, often turn out to be integer values, whole number.
So even if the underlying math looks continuous, the answers you get are often discrete. Like you can't ship half a box, so the math naturally gives you whole boxes.
Precisely. And that means these network models directly represent solutions to combinatorial problems, problems about selecting or arranging things which might seem totally separate at first glance.
So they're intuitive, but they also handle this tricky integer stuff naturally.
Yeah, Bertsekas calls them ideal vehicles for explaining fundamental optimization ideas, both continuous and discrete, because they just make sense visually and mathematically.
That does make a lot of sense. Okay, so with that foundation, let's talk about some of the core problems, the building blocks, really. Where should we begin? The shortest path problem seems fundamental.
Definitely. The concept is pretty straightforward, right? We have a graph, nodes connected by arcs, and each arc has a cost or a length. You want to find the minimum cost path from a starting node to an ending node.
Simple idea, but I imagine the applications are, well, huge.
Oh, absolutely huge. Think about data networks, routing packets over the internet. That's often a shortest path problem, trying to find the minimum delay or minimum length path.
And those lengths can change, right? Depending on congestion.
Exactly. The lengths can adapt. Another area is dynamic programming. You can often reformulate complex optimal control problems, finding the best sequence of actions as shortest path problems.
That's quite a leap from routing data to control sequences. What else? Anything maybe less obvious?
Well, project management is a classic one, figuring out the minimum time to complete a project.
Like with Gantt charts and critical paths.
Precisely. You model the project as a network, tasks are nodes, dependencies are arcs with durations. The longest path, which is found using shortest path algorithms on a related graph, determines the project completion time. And it identifies those critical activities.
The ones that if they slip, the whole project slips.
Exactly. So yeah, shortest path is everywhere, from the internet to making sure a construction project finishes on time.
And the book has that great analogy to help visualize it, the balls and strings thing.
Yes, that's a good one. Imagine the nodes are little balls, and the arcs are strings connecting them, with the length of each string equal to the arc's cost.
Oh.
Now, if you pick up the whole network by the starting node and let it hang freely under gravity,
Uh-huh.
the vertical height of each ball, its distance below the starting node, actually represents the shortest path distance to that node from the start.
Wow, okay. That makes it really tangible. What's the underlying math principle there?
It's related to something called complementary slackness, or CS conditions. Basically, it ensures that for the actual shortest paths, the strings are taut, you're paying the full cost. For arcs not on a shortest path, their strings might be loose. It's a neat physical intuition for the math.
Very cool. Okay, so shortest path is one pillar. What's another fundamental one? Max flow.
Right, the max flow problem.
Yeah.
Here, the goal is different. You're trying to maximize the total amount of flow. Think of it like fluid or data or goods that you can send from a source node to a sink node.
But you have limits, right? Like pipes can only handle so much water.
Exactly. Each arc has a capacity, a maximum amount of flow it can handle. You want to push as much as possible from source to sink without exceeding any arc's capacity.
And there's a key idea linked to this, isn't there? Something about cuts.
Yes, the famous max flow min cut theorem. This is really elegant. It states that the maximum amount of flow you can possibly send through the network is exactly equal to the minimum capacity of a cut.
And a cut is like drawing a line across the network.
Sort of. It's a way of partitioning all the nodes into two sets, one containing the source, the other containing the sink. The capacity of the cut is the total capacity of all the arcs going from the source side to the sink side.
Ah, so the bottleneck capacity determines the maximum flow.
Precisely. Finding the minimum cut tells you where the network's choke point is, and its capacity tells you the absolute maximum flow you can achieve. It's a really powerful duality.
Okay, so we have shortest path, minimum cost, max flow, maximum quantity. What about combining cost and flow? That sounds like the minimum cost flow problem.
You got it. This is often called the linear cost single commodity problem. Think of it as the classic transportation problem. You have supply locations, demand locations, and routes connecting them.
So nodes are cities or warehouses, arcs or roads or rail lines.
Exactly. And each arc has both a capacity and a cost per unit of flow. The goal is to satisfy all the demands from the supplies, respecting capacities, at the minimum possible total transportation cost.
And what does this really unlock? Why is this one so important?
Well, beyond just logistics, which is obviously huge, this minimum cost flow framework is incredibly versatile. Bertsekas emphasizes how it can model many other discrete or combinatorial problems.
Like which ones?
Things like the shortest path problem itself, actually, and another one called the assignment problem matching workers to jobs, for example. These could be formulated as minimum cost flow problems.
And the solutions stay integer.
Yes, that's a key property. Even if you solve it using methods that could, in theory, give fractional answers, for many important network structures like this, if your supplies and demands are integers, the optimal flow will also be integer valued. It really cements that continuous discrete connection we talked about earlier.
Okay, so those are some core building blocks, but networks get more complicated, right? What about when you have different types of things flowing?
Ah, yes. That leads us to multi-commodity flow problems.
Yeah.
Here, you're dealing with multiple kinds of traffic or commodities sharing the same network infrastructure.
Right.
Like, imagine telephone calls from city A to city B, and maybe video streaming data from city C to city D, all using the same fiber optic cables.
So each commodity calls, video has its own source and destination and needs to get through.
Right. Each has its own flow conservation needs. But the twist is they're coupled because they share the capacities of the arcs. The total flow of all commodities on a single arc can't exceed that arc's capacity. Or maybe there's a combined cost function you're trying to minimize. It makes the optimization much trickier.
Got it. And then there's another variation that breaks a basic assumption. Networks with gains. What's that about?
Yeah, this one challenges the idea that flow is always conserved. Usually what flows into a node must flow out, apart from the source and sink. But in networks with gains, flow can be diminished or amplified as it goes along an arc.
Amplified how?
Think about financial networks. If flow represents money, an arc could represent an investment that yields interest, so the flow increases. Or in, say, a water distribution system, an arc could represent evaporation, decreasing flow, or a pump, increasing pressure or flow.
Okay, that changes things. What's the most surprising consequence of allowing gains or losses?
What's really fascinating here is the behavior of cycles. In a normal network, flow just circulates around a cycle, but in a network with gains, a cycle can actually generate net flow if the gains around the cycle multiply to more than one, or absorb net flow if they multiply to less than one. It's a completely different dynamic.
That does sound like a whole different beast. Now, let's shift gears slightly to network problems with integer constraints. You mentioned these earlier as being tough.
Extremely tough, often. Discrete optimization in general can be hard, and network versions are no exception. They're often computationally very difficult.
Meaning it takes a ton of computer time.
Exactly. So much so that finding the absolute perfect optimal solution might be impossible in a practical amount of time for large problems. You often have to settle for approximations.
And the classic example here is the traveling salesman problem, TSP.
The infamous TSP, yes.
Right.
Find the shortest possible tour that visits every single node, city, exactly once, and then returns to the starting city.
Why is that specific problem so notoriously hard? It sounds simple enough to state.
It sounds simple, but it's, as Bertsekas puts it, far more difficult than something like the assignment problem we mentioned earlier.
How much harder?
Well, you can solve assignment problems with maybe hundreds of thousands of nodes fairly easily. The TSP. People struggle to find exact solutions for just a few hundred nodes.
Wow. What's the key difference that makes it explode in complexity?
It's this extra connectivity constraint. In the assignment problem, you're just matching pairs. In the TSP, you need to ensure all the chosen arcs form one single continuous loop, not a collection of smaller, disconnected loops. That requirement makes the search space just astronomically larger.
Okay, that makes sense. Any other interesting integer problems with a network flavor?
Well, there's the Chinese postman problem. This one asks for a cycle, but instead of visiting every node once, it needs to traverse every arc of the graph at least once, aiming for the minimum total distance.
Chinese postman, why that name?
It's related to the problem of a postman needing to walk down every street in a neighborhood to deliver mail and wanting to minimize their total walking distance.
Ah, and this connects back to older math, right?
It does. It has a direct historical link to the famous Königsberg Bridge problem, posed by the mathematician Euler way back in 1736.
The one about crossing bridges without repeating?
That's the one. Euler's work on that puzzle is often considered the very beginning of graph theory. The solution involves finding what we now call Euler cycles or Euler tours, which are exactly what the Chinese postman problem looks for under certain conditions. It's a nice link between history and modern optimization.
Cool. So we have all these different kinds of problems. How do we actually solve them? What's in the algorithmic toolkit?
Bertsekas broadly categorizes the main approaches. You've got primal cost improvement methods, dual cost improvement methods, auction methods, and then local search heuristics, especially for those tough integer problems.
Okay, let's break those down. Simplex methods. That sounds familiar from general linear programming.
It is. The simplex method, pioneered by George Dantzig, was actually first specialized for the transportation problem, a type of minimum cost flow problem back in 1951.
And what's the key insight for networks?
Well, it systematically moves between adjacent corner point solutions, always improving the cost. And critically, for many network problems like min-cost flow with integer supplies and demands, the simplex method is guaranteed to find an optimal solution that is also integer. That's huge.
Right, avoids those fractional answers we don't want. Okay, what about dual ascent methods?
These work on the dual problem. Instead of directly adjusting the flows, the primal variables, they iteratively adjust node prices or potentials, the dual variables, to improve a related objective, the dual cost.
Try to find the right prices. How does that help?
Getting the dual prices right indirectly guides you towards the optimal primal flow solution. One famous approach is the primal dual method,
Also known as?
the sequential shortest path method. It's rooted in Kuhn's Hungarian method for the assignment problem from 1955 and was extended by Ford and Fulkerson. It basically tries to find the steepest improvement in the dual cost at each step by solving shortest path problems.
Okay, is that the only way?
No, there's also the relaxation method. This one is often faster in practice, even though it doesn't always pick the absolute steepest ascent direction. It relaxes some constraints temporarily to make faster progress.
Interesting trade-off. Now, thinking bigger picture, what's a key advantage of these dual methods, maybe compared to simplex?
A really important advantage, which they share with auction algorithms, is in reoptimization.
Meaning?
Meaning, if you've solved a problem and then the network changes slightly, maybe one arc cost changes or one capacity, these methods can often reuse the previous solution or the previous prices as a starting point.
Ah, so they adapt quickly.
Extremely quickly, often. They don't have to start the whole computation from scratch like simplex usually does. In dynamic situations where things change, that's a massive benefit.
Makes sense. Okay, you mentioned auction algorithms. That sounds intriguing. Who came up with those?
That was actually Bertsekas himself back in 1979, initially for the assignment problem.
And what's the core idea? Is it like a real auction?
It really is. It's inspired by market bidding. You have, say, persons bidding for objects. The bids increase the prices of the objects, and eventually an assignment is made based on who values which object most relative to its price.
That's a very different way to think about optimization. How efficient is it?
It can be very efficient, especially with techniques like epsilon scaling. This basically involves working with slightly approximate prices initially, which helps the algorithm make rapid progress, and then refining the precision over time to guarantee optimality. It sounds counterintuitive, but allowing a bit of approximation early on helps it converge faster overall.
Clever. Okay, and finally, what about those really hard integer problems like the TSP, where exact methods might just take too long?
That's where local search methods come in, or sometimes called heuristics.
Heuristics meaning rules of thumb, educated guesses.
Kind of. They don't guarantee finding the absolute best, globally optimal solution. But they aim to find a good solution, hopefully close to optimal, in a reasonable amount of time. They often provide substantial improvement over just picking a solution randomly or using a very simple rule.
And what are some examples of these heuristic approaches?
Well, there are genetic algorithms. These are inspired by biological evolution.
How so?
They maintain a population of potential solutions and iteratively improve them using operations like crossover, combining parts of good solutions like genetic splicing, and mutation, making small random changes to generate new, hopefully better solutions.
Survival of the fittest solutions, basically.
Pretty much. Then there's simulated annealing.
Annealing, like in metallurgy, cooling metal slowly.
Exactly like that. It uses a concept called temperature. Initially, the temperature is high, and the algorithm is allowed to sometimes accept moves to worse solutions.
Why would it do that? Isn't the goal to improve?
It is, but accepting occasional worse moves helps the algorithm avoid getting stuck in local minima.
Oh, those little dips that aren't the true lowest point.
Right. By sometimes jumping out of a small dip, even if it means temporarily going uphill, it has a better chance of exploring the wider solution landscape and eventually finding the true global minimum, or something close to it. As the temperature gradually decreases, it becomes less likely to accept bad moves and settles down.
Fascinating analogy. Any others?
One more Bertsekas mentions is rollout algorithms. These are a bit different. They build a solution step by step, incrementally.
How?
They use a simpler, faster base heuristic to look ahead one step, or maybe a few steps, and decide the best immediate move to make, ensuring sequential consistency or sequential improvement at each stage. It's like playing chess by thinking one move ahead using a simple evaluation, but applying that thinking carefully at every single turn.
Okay, that's quite a toolbox of algorithms.
It really is, from exact methods like simplex to sophisticated heuristics like simulated annealing.
So that brings us towards the end of this deep dive. We've journeyed through, well, quite a lot, from the basics like shortest path and max flow.
To more complex ideas like multi-commodity flow, networks with gains, those tough integer problems like TSP.
And then explored this diverse arsenal of algorithms designed to tackle them: simplex, dual methods, auctions, heuristics, each with its own way of working, its own strengths.
And it's crucial to remember this isn't just abstract math. This field, network optimization, it really does underpin so much critical infrastructure and decision-making.
Like you said, the internet routing, Google Maps for your commute.
Global supply chains, managing inventory and shipping, airline scheduling, power grid management. The list goes on and on. It's quietly working behind the scenes in countless ways.
But as the author, Bertsekas, points out, there's often no universally best method, right? The best algorithm can really depend on the specifics of the network, its size, its structure, its diameter, as he calls it.
Absolutely. Context matters a lot in practice.
So maybe a final thought for you listening. Try thinking about how these abstract ideas of networks, flows, costs, and optimization might apply to networks in your own life.
Yeah, that's interesting. Like your daily commute isn't just about roads, but maybe about time versus cost versus stress.
Or information flow in your workplace, or even maybe the network of personal relationships.
Mhm.
Where could thinking in terms of optimization, nodes, arcs, flows, and costs offer some surprising insights? What might you be implicitly trying to optimize already without necessarily putting these labels on it?
That's a good question to ponder. What are the hidden networks and flows we navigate every day?